We remember that electromagnetic radiation is a coupled oscillating electric field that induces an oscillating magnetic field. So remember, the electric field is a vector, so it has a direction. So the electric field in light is oscillating in a particular direction. We call that the direction that the electric field is pointing, we call that the polarization of light. We know that the magnetic field is perpendicular to the electric field, so if we know the direction of the electric field, then we know the direction of the magnetic field. Now, most of the light that we see and deal with every day, sort of ordinary light, is unpolarized light, which means that the direction of the polarization, the direction of the electric field, is sort of randomly distributed over all directions. So the electric field of the different photons all point in different directions. So sunlight, light bulbs, most of the light that we see is randomly oriented and is this unpolarized light. However, a few things, like lasers, for example, produce polarized light. Here, the electric fields are all pointing in the same direction. So lasers are polarized, liquid crystal displays, and certain reflections. So some lights reflected from low angles, from mirrors or water, is partially polarized. So in this case, all of the light is oscillating in one direction, and in this case, the light is all polarized, so that electric field is all oscillating in the same direction. So some lenses are what we call polarizers. Polarizers are made out of mostly clear plastic sheets and that are made up of long chain molecules that are stretched out in one direction. And they are chemically treated so that they are conducting in one direction, but not in the other direction. The result of this is that if light travels through this polarizer and the electric field is in the direction of the conducting molecule, the photon is absorbed. However, if the electric field of the light is perpendicular to the molecule, then the light goes straight through. That means that if the light has an electric field in one direction, it goes through, but if it's in the other direction, it's blocked. So the light that is transmitted through the polarizer is now polarized. Notice this means that the intensity of the light, if it starts out as an ordinary unpolarized light, the intensity decreases and it ends up being half the original intensity. But now the light is polarized. So why is it half the intensity? Well, to see this, we'll use an analogy with a waving rope going through a picket fence. The picket fence is like the polarizer. It lets the rope oscillate when it goes in one direction, the direction of the pickets, and it won't oscillate when you try and make it oscillate when you swing the rope perpendicular to the pickets. So remember, the electric field is a vector, so what happens when the electric field goes through the polarizer is that the component of the electric field that is parallel to the direction of the polarizer goes through. So if a wave with an angle of 45 degrees goes into the polarizer, then what comes out would be polarized, and it would be the y component of that electric field. So it'd be the vector component that goes through. So it's not like, a dog with a big stick trying to go through a door, where it either goes through or it doesn't. It can partially go through if that angle is at an angle. The light isn't just blocked, or not blocked, rather, part of it goes through. And unless the light is completely polarized at a 90-degree angle, then some of that light will get through. So in the picket fence analogy, if the rope is swung in the same direction as the gap in the pickets, then all of it will go through. If the rope is swung at 90-degree angle, none will get through. But if it's sort of swung at an angle, then some of that wave will still make it through. Okay, so let's look at polarization more quantitatively. If unpolarized ordinary light is shined onto a polarizer, then the light that makes it through the polarizer is half the intensity of the original light. So here, light transmitted is equal to 1/2 I incident. So the incident light is the light that hits the polarizer, and the transmitted light is the light that goes through and makes it through the polarizer. So the light is unpolarized, half the intensity out that goes in. If we look at the case where the polarized light shines on a polarizer, then the intensity that is transmitted, that comes out of the polarizer, is equal to the incident light times the cosine squared theta, where theta is the angle between the polarization of the incident light and the direction of the polarizer. So if theta is 0, then that means the polarized light is aligned perfectly with the polarizer. So the cosine of 0 is 1, and 1 squared is 1, so all of the light goes through. That makes sense in our picket fence analogy. If they are aligned, then the light doesn't notice, it just goes straight through. If the angle is 90 degrees, then the cosine of 90 is 0, so the transmitted light is also 0. This also works with our picket fence analogy. If we swing side to side, none of the waves go through. If the light is at an angle, then we do the cosine squared. So if the angle was 45 degrees, then the cosine of 45 degrees is the square root of 2 over 2. So we square that to get 2 over 4, or 1/2. So that should sort of make sense. If the angle is 45 degrees, then exactly half the intensity makes it through the polarizer. So to do the cosine theta squared, you do the cosine, and then you square that value to get the cosine squared. So that means if we have two polarizers, our first polarizer will polarize the light in one direction, and the block will have half the intensity, and the second polarizer will block the light that isn't aligned, so it will block a cosine squared theta of the light, where theta is that angle between the two polarizers. So in total, when we have two polarizers, the transmitted light is equal to 1/2 the incident light times the cosine squared theta, where theta is the angle between the two polarizers. So one place where you run into polarizers is in polarized sunglasses. Polarized sunglasses are polarized, so the incident light is unpolarized, but half the light intensity goes through and half is blocked. But the cool thing about polarized sunglasses is that light reflected at low angles becomes polarized. When light bounces or reflects off of a surface, light where the electric field is parallel to the surface is reflected, while if the light is perpendicular to the surface, then it's not reflected. So especially with low angle scattering, like light coming off of a body of snow, a body of water or some snow, the polarization of that reflected light is horizontal. Polarized sunglasses are polarized vertically, so the reflected light is completely blocked. So if you were looking at a lake or the ocean, or the reflected light, that reflected glare, will be completely blocked, while you can still see what's going on pretty well. Another use of polarized glasses is in 3D glasses. I guess I don't know when will be allowed back in theaters, but what happens is that the polarization in one lens is in one direction, and the polarization in the other lens is in the other direction. That means that by polarizing the light from the projector and reflecting them off the screen, so then each eye will see a slightly different image, so you can kind of trick your viewer into thinking that they are seeing something in 3D because you're seeing something different in each eye. Okay, so we have an example here. A beam of unpolarized light with an intensity of 0.2 watts per square meter is shining through a polarizer. Well, what's the intensity of the light that comes out? Well, this one's a piece of cake, right? So here it's just unpolarized light going through a polarizer. So the transmitted is equal to half the incident. So the incident light here is 0.2 watts per square meter. So our final answer is 0.1 watts per square meter. Piece of cake. The next example, we have the polarized light with a beam of intensity of 0.1 watts per square meter is incident on a single polarizer where the electric field is at an angle of 20 degrees to the axis of polarization. So we want to know the intensity of the light here. So in this case, the I transmitted is the I incident times the cosine squared theta. So the I incident is 0.1 watts per square meter, and its cosine squared of 20 degrees. So we do our math on this, and we get our transmitted intensity is 0.0883 watts per square meter. So you'll notice most of it gets through, right? But like 88% gets through because that angle is relatively small. If this was a case with two polarizers, then remember the first polarizer would block half the light, and then the second polarizer would block the cosine squared theta of that light that makes it through the first polarizer, so then it would be 1/2 times the cosine squared theta. But in this case, we start with the polarized light already, so we don't have to worry about that. All right, so you have a few questions to do, so good luck with that, and then we'll finish the unit with a look at the Doppler effect. Good luck.